Hello, greetings to everyone and welcome this video lecture on cosmology. In the last lecture we saw the special theory of relativity concerned with the objects or systems which are either at rest or moving at constant velocity. Assuming two postulates, first that all inertial frames are to be regarded as equal, that there exists no absolute frame of reference whatsoever, and in the second postulate, velocity of light as a universal constant that is the same in all direction and in every inertial reference frame, independent of the frame's motion, we see that how it affected contraction of length, dilation of time, and increase of mass with velocity. In this lecture, we see how this has further affected a radical transformation of Newtonian concept of space and time into space-time. And then we shall look into the curious view of the world with the general theory of relativity. Let us look into what is the radical transformation of Newtonian concept of space and time into space-time by special theory. In our experience, something exists at some place and at some time. We think of space and time as separate. So also was the conception of space and time in Newtonian physics. Suppose we wish to say where and when some event has occurred, say an explosion in an aircraft. We will have to mention four dimensions: the latitude, the longitude, the height above the ground, and the time. The first three of these give position in space, while the fourth one gives the position in time. The first three are called Cartesian coordinates. But the theory of relativity with its two postulates has effected a radical transformation of the Newtonian concepts of space and time into space-time continuum. According to Einstein, space and time are not separate. There is no such a thing as space and time. There is only space-time. It is accomplished by modifying the meaning of simultaneity, which is the common property of space and time. For if moving clock in different frames of reference run differently, then it is clear that time relation like now, sooner, later, and simultaneous are merely relative local terms. What is sooner in one frame of reference may be later in another and simultaneous in a third frame of reference. Two events which are seen to be occurring simultaneously by one observer may occur in different temporal sequences for other observers in different frames of reference. This implies that objects and events in the universe do not have a shared now, a universal time as held by Newton. There is no correlation between here now and there now, but only between here now and there then. From that perspective, it is clear that we cannot relate our present instant with any other instant at a long distance. The original meaning of the word present thus is both spatial and temporal. Moreover, the space and time reckonings are no longer independent of each other. If you alter the way of reckoning position in space, you will also alter the time interval between two events. If you alter the way of reckoning time, you may also alter the distance in space between two events. Thus, space and time are no longer independent any more than the three dimensions of space are. Hence, we need four measurements to determine the position of an event. That is the essence of what is meant by the substitution of space-time for space and time. Thus, according to the theory of relativity, Physical reality is four-dimensional, and the fourth dimension is time. We exist in a four-dimensional space-time continuum. Now, how are we to apply this space-time concept of our universe to the so-called or to the accepted theory of the Big Bang regarding the origin of the universe? Currently held theory of Big Bang, presupposing a beginning for the universe, questions the reality of time and eternity. The theory of relativity, which is showing the intrinsic connection between time and space, takes us further to the reality of the space-time conception of the physical world. Also can be questioning the space-time conception for the beginning of the universe. In fact, as we have seen, according to the theory of relativity, time could not be considered, or time could be considered as the fourth dimension of space. Going back to the origins of the universe, it is found out that time did not exist before space. They came to exist simultaneously. That's why we read that St. Augustine asserted, God made the world with time and not in time. By regarding time as part along with space in the existence of the physical universe, rather than something in which the origin of the universe happens, we see in perspective the intrinsic connection between time and space. Thus, God, time and space are together, one concept of the universe. To have a pictorial image of this reality, we can represent space-time by a diagram with the time drawn vertically and space horizontally. The future is toward the top of the diagram, past toward the bottom. We could draw this diagram in a sheet of paper. Suppose we take a sheet of paper. If space and time were infinite, we would need an infinite sheet of paper for our diagram to represent space-time property. However, if time is bounded in the past, that is, then the diagram must have a boundary somewhere along the bottom. We can imagine cutting a horizontal edge. Suppose we take time and space. Time something horizontal and vertical in that way. At this stage, we can imagine cutting a horizontal edge somewhere. It may also have a future boundary if you make a similar cutting along the top. If you have a boundary line of time in the future at top, and in the past it's down at cutting. At this stage, we can entertain the fact that space is not after all infinite, giving space to the beginning of the universe. Now, thinking in a thought experiment along with this understanding of the Big Bang, origin of the universe, and Einstein was the first to point out that space might be finite yet unbounded, and the idea remains a serious and testable cosmological hypothesis that the space might be finite yet unbounded, not infinite. And in his suggestion, this possibility could be accommodated in a diagram by rolling the sheet. Now we have time and space, infinite time and infinite space, which requires infinite sheets of paper. Now, how to accommodate a finite time with the space unbounded? That he would say that by rolling the sheet around to make a cylinder, it is like a cylinder. Time is always unbounded, and time space here is inside unbounded and finite. And thus space at each instant is now represented by a circle. At each instant is represented by a circle. If we transform the circle, this cylinder, into a cone, that is like this, into a cone, we will have then a better picture of the expanding volume of space. It made similar to the expanding universe. That will accommodate very well to the Big Bang hypothesis that the universe originated in a singularity of infinite compression. And that is depicted here by allowing the cone to taper to a single point at the base. The singular apex of the cone represents the abrupt appearance of both space and time in a Big Bang. Abrupt and expanding, all over expanding like this. This from here and expanding all over from a single point at the center and expanding all over. This gives the idea of a cylindric, unbounded, finite space-time with the Big Bang beginning of the universe. Having accommodated space-time concept in special theory of relativity even to the Big Bang theory of the origin of the universe, now let us move to general theory of relativity. Though the special theory of relativity had remarkable consequences in our concept of physical reality, the impact of the general theory of relativity was much more spectacular. It changed forever our view of the universe. It is very important in our study of cosmology to know the spectacular and some curious view of the world with this general theory of relativity, as it gives a different picture of the universe as one single dynamic entity with all basic concepts of matter, space, time and motion into that one entity. The general theory is nothing but the extension of the principle of relativity to other aspects of nature. We know that in his special theory, Einstein was concerned with uniform, non-accelerating frame of reference without gravitational field. But in the general theory, his preoccupation was frames of reference with accelerated motion and gravitational motion. He noted that the effects of accelerated motion and gravitational motion are indistinguishable. That is to say, there is no way of distinguishing between accelerated motion and a constant gravitational field. Therefore, he announced the principle of equivalence regarding both, that gravity is equivalent to acceleration. How is it? To be more clear about it, we need to know how the concept of gravitation for Einstein is and how it differs from that held by Newton. Newton viewed gravity as a force of attraction between bodies acting at a distance. For instance, things fall to the earth because the latter attracts them. That is, earth attracts bodies, that's why that bodies falls on the earth. It is according to Newton. But according to Einstein, in general theory of relativity, gravity is a property of space and a distortion that happens in space-time. It is neither a force nor an attraction. It is the warping of space-time on account of the presence of matter or energy. It is a geometrical property or a distortion that happens in space-time in a geometrical nature. The curvature in the geometry of space-time that happens. That is to say, the presence of mass curves space. Thus, a gravitational field is really a curving of space. The greater the mass or energy, the larger the curvature of space in its vicinity. In their essence, the equation of general theory regarding the gravitation would be stated as geometry is equal to matter plus energy. If matter or energy exists, it acts as a source for the geometry. Thus, gravity is not a force but geometry of matter and energy in space-time. It is the geometrical property, a curvature of space-time. We can understand space-time curvature in the presence of a massive body by comparing it to a sheet of rubber stretched flat. Just imagine a rubber is stretched flat. Now, in the stretched flat rubber sheet, a massive object is put, but that distorts the sheet by stretching the locally forming a curve or a warping the sheet. The amount of distortion or curve or warping depends on the mass of the object. Thus, it is not the case as Newton proposed that planets move in curved paths around the Sun because the Sun exerts a gravitational force on them to turn them away from their natural tendency to move in straight lines. It is clear then that gravity is not a mysterious force acting at a distance through space. Rather, it is the presence of the massive body, the Sun, warping or curving the space-time continuum in its vicinity, and the planets merely follow the easiest route. So, just like a massive body in the rubber sheet, the Sun, a massive body in space-time continuum, makes a warping all around it, and in the warping made by the presence of the Sun, the other planets around the Sun falls to the easiest path of moving around with its own heaviness. Thus the planets merely follow the easiest route possible around the Sun in the space-time curvature due to the Sun's heaviness. And this easiest route turns out to be something similar to the forced route taken by planets according to Newton's theory. So Newton mistakes the easiest route within the curvature or the warping of the space-time with the Sun as the forced route, as some force is applied or the attraction of the body to another body. It's a mistake of Newton. The space-time distortion or curvature deflects the planets, and the planets moves in curved paths. While moving in curved paths, it makes its own grooves, its own local curvature or warping, and moves around the Sun. It is as though the Sun making grooves around it, warping space-time in its vicinity, and the planets moves in these grooves. Now, the presence of the massive body, the Sun stretching space-time, sets up trajectories around it, and planets move along these trajectories. What are these trajectories? The trajectories can be represented by supposing the path of ball bearings of different masses rolling over the rubber sheet. Now imagine the rubber sheet that we earlier imagined, and in which there was a heavy matter which made a warping around it. Now in that local warping of the heavy body in the rubber sheet, just think of the ball bearings of different masses are put, and how these ball bearings of different mass will be rolling over the rubber sheet and trapped in the deep well surrounding the heavy body in the rubber sheet. It will be the similar way we can imagine about how the planets moving around the Sun in the warping made in the space-time. And such trajectories of the planets are called geodesics. In the case of the falling apple, the apple is not drawn to the earth by any force, but is merely rolling into the local space-time well created by the earth. That is the explanation for why the things fall down on the earth. Because with the earth, with its own heaviness, there is a local space-time well. and anything and everything within that will fall or move within that space-time well. And that is the nature of the space-time well, which is a geometrical, is the reason of apple falling on the earth. Now, understanding gravity as a property of space, that it is a distortion that happens in space-time on account of the presence of matter or energy, which is called warping or curvature of space-time. Now, how are we to explain, or in order to understand Einstein's general theory explaining that accelerated force and gravitational forces are not distinguishable from each other? In order to understand that, suppose some people are in a rocket traveling out into space. They have no weight since they are beyond the gravitational field of the earth. When the rocket accelerates in the forward direction relative to the distant stars, they are pushed back against their seats. And when the rocket decelerates, they are thrust forward. It is just as what happens with us when we are traveling in a bus. That when the driver applies acceleration, we are pushed back against our seat, and if the driver applies sudden brake, then we are thrust forward. Similarly, the people in the rocket would usually associate the pressure backward with an acceleration of the rocket and the thrust forward with the deceleration, as that it may be thought of applying brake to the speed of the rocket. And when the rocket is neither accelerating nor decelerating, they do not experience any effects. Now, suppose along with that, imagine that while they are journeying along in space with a constant velocity to the distant stars, a stray planet comes along. Let us know that it is not seen by anyone in the rocket. But with the planet in their vicinity, the people in the rocket are pushed to the back of their seats. Since they do not know the presence of the planet, and the effect is the same as if the rocket accelerated, they will erroneously or mistakenly conclude that the rocket was accelerated or that it has taken a sudden speed. But it was a mistake. It is a mistake to suppose like that. Now the question is there any way they can tell whether the forces they feel are due to acceleration or due to the gravitational pull of a nearby mass or nearby planet? The answer is that there is no way of distinguishing between the two. That is what Einstein observes. Einstein was struck by this equivalence of acceleration and gravitational force, which are indistinguishable. He stated this fact of the nature experimented in the principle of equivalence, that at a single point in space, the effects of gravitation and accelerated motion are equivalent and cannot be distinguished from each other. One of the consequences of the equivalence of gravitational force and accelerated force is the bending of light rays by the presence of huge masses such as stars or planets. Gravity bends light waves. For instance, the light of stars passing very close to the sun would bend inwards to the sun. This happens because the light beam is affected by the curvature of space in the vicinity of the sun. It is basing on this fact of the general theory Einstein predicted that gravitational fields bend light beams, or light beams are bent by gravitational fields. The prediction was verified by measuring the deflection of starlight by gravitational field of the sun. Thus, it was accepted. Now, having explained this general theory of relativity and taking the view of the universe through the general theory, we understand that Our universe is one in which fundamental concepts of space, time, matter, and motion are inextricably linked. They do not exist independently of each other. That is the general view of the world through general theory of relativity we get into. There is no empty space-time existing independently of matter and motion. Hence, it could be deduced of the universe in general that if all matter or energy were removed from the universe, what is left behind would not be empty space-time but absolutely nothing. But thus the space-time of special theory has turned out to be the space-time of matter and motion inextricably linked to each other. That is to say, there is no matter and motion without space-time, or there is no space-time without matter and motion. Or that everything is linked to each other as one entity. Moreover, in contrast to the homogeneous causally passive space and time of Newton and the inert space-time of special theory, the space-time of general theory is heterogeneous. Space-time turns out to be an active player in the cosmic drama, telling matter how to move. Very interesting. And matter moving in turn affects the curvature of space-time relative to the force acting it. Thus, we understand space-time is a dynamic quantity interconnected with the forces acting and bodies moving in it in such a way that space-time not only affects but also is affected by happenings in the universe. Hence, space-time, that is space and time, is not anymore a mere fundamental absolute within which we are to organize our experience. It is also at the same time our experiences influencing space-time to be a dynamic quantity that the universe as such is. So it is not space-time in which our experiences are organized, but rather it is also our experiences getting or influencing space-time and making it to be more dynamic a quantity as the world as such is. Accordingly, if we are to answer the metaphysical question with which the ancient Greek thinkers like Thales were engaged in philosophizing at the beginning of philosophy, that what is the ultimate stuff or substance of the material universe? According to, by knowing the universe with general theory of relativity, we can answer that. The answer would be very clear that it is nothing but the dynamism of space-time continuum. Along with it is involved of the conception of motion. From the relativistic perspective, motion is quite different from that of the classical understanding. It is not anymore as displacement of the unchanging particles or particles with a constant mass and volume in a static absolute space. Rather, it is the disappearance of a local curvature in one region and its reappearance in a neighboring region. This creates for our senses an illusion of displacement of a passive material in an equally inert space as is conceived in classical mechanics or Newtonian physics. Further, we can notice that general theory has brought about a paradigm shift in the concept of motion from Aristotle to Einstein. For Aristotle, force is needed to keep a thing in motion. That is to say, a thing moves only insofar as and as long as it is moved by another or another body, another force. And for Newton, force is gravitational force between bodies, in which bodies are in uniform motion in a straight line so that it does not require force. Other than this, he noticed that if at all we experience a force apart from this gravitational or uniform motion, that if anything is to be moved outside the uniform motion, then force is needed for accelerated motion. But for Einstein, in general theory, both the accelerated and gravitational forces are abolished and replaced with the curvature of space-time. Thus, to conclude, with the theory of general theory of relativity, in our present understanding of the universe based on the theory of relativity, it is interesting to see the metamorphosis or the progressive stages in transformation of the cosmological categories from Aristotle to Einstein. At first, we see it as Aristotle who enunciated the categories of cosmology by which we explain the universe in Western philosophy, namely matter and form, quantity, quality, space, time and motion. At the second stage, we see how it got transformed with Newton. Newton eliminated the form in Aristotle together with the quantity and quality. Then what he did is that he transformed the concepts of motion, space and time to make it appropriate to his mechanistic conception of the world into four homogeneous absolutes existing independently of each other, namely matter, space, time and motion. At the third stage, we have the present paradigm shift from Newton's mechanistic conception to Einstein's theory of relativity, wherein we find absolute character of Newtonian categories are abolished and transformed to a view relative to each other. That is to say, Einstein in the special theory of relativity made space and time relative to each other, converting them into space-time, which turned out to be the absolute constituting background of the universe with the special theory of relativity. But in his general theory of relativity, space-time itself was rendered relative to matter or energy. That is to say, the geometry of space-time is determined by the distribution of matter or energy. This resulted in the unification of the four categories of Newtonian cosmology into one single or singularity called geometry. The universe is nothing but a geometry of space-time matter energy of relativity. Thus, the French historian and Indian scholar Amaury de Rincourt writes, "This universe of classical physics has been swept away by relativity, whose main hallmark is unification, joining together in an indissoluble bond of space, time, energy and matter." Thus, the theory of relativity with Einstein, we have a view of the world, a world in a single unity of geometry with space-time, energy and matter together, relative to each other. And having got a picture of the universe of our present day, we will look into the origin of the universe in the next lecture. Thank you.